Hello everyone, welcome back to Tux Riders. In the second video of the FreeFEM series, we want to have a look at some of the built-in features of FreeFEM for 2D mesh generation and handling. Let's go for it. Okay, so in the previous video we covered the language syntax and most essential basic ideas of FreeFEM. In this video we want to talk about 2D mesh generation. It's quite powerful and simple, some prototyping features available in FreeFEM for 2D mesh generation. There are also 3D capabilities that we will cover in the next video. Similar to the previous video, we have a couple of examples here, and we want to go through them one by one, and they go from the most basic one to the more advanced level, let's say. There are more features available in FreeFEM for sure, but I think these are the most essential things that are quite, handy in projects. So let me start with the first example that is actually for the most basic form of mesh generation inside FreeFEM. So this is example 1. I open a new terminal. I go to the folder where I have these examples. So here, yeah. And then the first example is actually example 1. Example 1 is the first example is this one. I can run it with FreeFEM++ in example 1, name of the file and EDP. So I talked about this in the previous video about a file extension and a way that we can run FreeFEM programs. So as you can see here, we have a very simple statement that says that please create a square for me. And that will be square 1 by 1. So the dimensions are not mentioned here. When we don't pass any dimension or let's say movement arguments that you will see in a second example. When we don't pass any of those parameters, it creates a square with the dimension of 1, so 1 by 1. And these numbers are actually mesh size. So this is the number of mesh along the x-axis, and this is the number of, let's say, number of elements along the y-axis. And then we have a built-in function called plot that can be used to plot a mesh or plot a finite element space. You will see in the next videos about it. And then there are a couple of arguments to pass to that, and then one is wait, meaning that please wait on it, otherwise it goes through, it doesn't wait on this function calls, and if there are more plot statements, plot commands in the code, the FreeFEM always plots the last one. So when we say wait, it means that, yeah, at least keep the plot. Although the program continues execution, but at least the plot will be kept there. So let me run the example and we see what I mean. But this is square, so this is 1 by 1, and this is the plot window of FreeFEM. There are a couple of shortcuts that I will mention later that they are useful, especially for finite element visualization. But at this moment for mesh, we don't need to press any key, and this is the default behavior is okay. So you can see that we have 4 elements here, and then 5 elements along the y-axis, and this is actually the output of these kind of commands. And then in the example 2, you can see that we can have more advanced usage of square. So you can see that I have 2 integers here, n and m, that are for numbers that are passed as the first 2 arguments. And then it accepts a kind of array-like notation here. You can see the first one is for x, that is multiplied by the built-in function x and built-in function y. And then you can see that it says that actually this is a size. When you multiply x by something, that's a size. That is actually x0 minus x1. So these are actually x0, x1, the coordinate of the first point, and then x1 and x2, the coordinate of the other point along the diagonal of the square. So you can see that this is a size, and then we add the initial, the x value of the first point to that. So this is when you add something to x, it's the movement of the mesh, and when you multiply something by it, it's actually the size. So this is the way that you can control the size and location of the square when it's generated. So now I run this example, and you see that you don't see any major difference. That's only the sizing, the mesh size, let's say. But if I start to plot, for example, XY values of this, or start to assign something to that in more advanced visualization software like Paraview, you can see the coordinates that this is actually moved, and x0, y0 is here, and x1, y1 is here. So because it's usually, it's the rectangle usually starts from the origins, it doesn't really matter that this x0 is usually 0, so you can easily multiply the size by x and add the movement, the amount of shift that you want to it using this notation. And then this is the most basic form of 2D mesh generation. There is one more advanced kind of notation in FreeFEM. In example 3, you can see that, and that's actually, a sort of parametric design of borders, parametric definition, and it's quite common in a lot of software programs to work with these kind of notations. So we first say that we want a type mesh. That was also, here it was also mesh. You can see the mesh th equals something, but here we will have like another name for the mesh. It doesn't really matter at all. So we have 4 borders. So we are going to create a kind of square again, or rectangular domain. So here we have 4 borders, and each border is constructed using a parametric definition. So we say that for t from 0 to 1, this is the definition of the first border. So for a rectangle, it is the bottom edge, that the y is 0, and then we change x like L multiplied by t, and t from 0 to 1. And it means that the x changes from 0 to L. And L is actually a real value I have defined here. I want to have a rectangle, let's say square, with the edge size of 0.1. And then for the next edge that should be connected to B1, it is defined like this. You can see that x equals L, which defines actually the edge, on the right edge actually, and then y changes from 0 to L, because it's L multiplied by t, is t from 0 to 1. And then for B3, which is the top edge, it changes from, x equals L to 0, because you can see that this is actually the definition. And then we define the left edge, that it starts from top to the origin. So this is actually the way that we can design it, and the main advantage is that you can assign different labels to each edge. So here you can see that it's actually coming from a kind of CFD computation, that we have a flow from left to right. And then you can see that for the bottom and top edge, we have the label for wall, and wall is defined here as 1, it doesn't matter. Later on we want to solve a PDE. You can see that these labels can come into play, but at this moment they should be different, and that's enough. And then for the label, when it is right, it is outlet, and for the inlet on the left. So this is the way that this kind of parametric design can help. And this is one advantage. The second advantage is that it allows you to define any kind of geometry you like, And then after defining these borders, we say that mesh equals build mesh, and build mesh is a function. You can see that this is parentheses, and then you pass all the borders like a kind of function call, but this is not actually a function, with the size that you want to assign the number of elements on that border. So in this case, I assign an equal number, same value for all the borders, but it shouldn't be necessarily the same. You can assign any value, and the built-in mesh generation of FreeFEM handles that automatically. It's called in BAMG. It handles that, and it generates really nice meshes, let's say. And then I plot a mesh with a weight 1, although we don't have any more plot statement here, so it doesn't really matter. And then mesh size is 60, so it's going to be a kind of, coarse mesh, let's say. Fine mesh. Okay, so for this is example 3. And as you can see, this is actually the mesh that we generated. Let's change, for example, one of these elements on, for example, I say 30. And then for the border 2, which is the left, which is the one on the right, I multiply it by 2. So you will see that we will have more elements here. So here there are 30, and here there are 60. Okay, so let's go to the fourth example. That's a semicircle. So in addition to creating like straight lines, we can have like curved lines that are defined using trigonometric definition. In this case, we have a line that is a semicircle that is defined by some parameters that you can see they are very small. This is a mesh that we will use later in one of the projects that we want to discuss in TuxRiders. And you can see that the mesh size is really small, micrometers sort of scales. And then here we have another straight line that is defined using another label. You can see that here we have labels built in, so same label for both edges, meaning that later on we want to assign the same kind of boundary condition to both edges. And then we define a kind of mesh controller here, and then we have 20 multiplied by that mesh number. This is also another common way of defining mesh in finite element computation, mesh size, sorry, I mean. And then we plot the mesh. So let's check the results of this example. So it will be like example 4. And yeah, as you can see, this is actually the result. This is the curve that is produced using trigonometric functions, parameters, let's say, parametric definition, and this is the straight line. And then we specify different numbers for this. As you can see, that this is 10 by n, and this is 20 by n, because we need more elements on this curvy part in comparison to straight line. And then let's make it more interesting. We go to the example 5. In which we will have, the previous definition for the semicircle, the same definition, but then we have another circle inside it. So this is the way that you can easily define any kind of circular path inside FreeFEM. And then we will have like x center and y center for that. And here you see that it's much smaller because we have like here the diameter for P, which is actually the hole, let's say, or pore in this case. And then we pass that one as to the built mesh function as well. So you can see that we built a function that is we built a mesh that has actually 2 borders, and then another border, third border, which is embedded inside. So let's see what happens. And as you can see here, we have another label, so label 3 for that. So let's see how it works here. So example 5. And this is actually this is one of the ways that we can define subdomains or regions inside FreeFEM. Let's say, for example, for a simulation that we want to have different diffusion coefficients inside only a subdomain of the mesh. You can see that the red one was one region and this is another one. And this is generated because we have 2 different mesh. One is embedded of another. So this is one way of doing that. And then even more interesting is like, the same code, this is the same code exactly, example 6 and example 5, but there is only one difference. Can you see it? It's here actually, it's minus 20. So for the border B0, we pass minus 20 in example 6. And by this nice definition, by this nice notation and syntax in FreeFEM, we can define like mesh subtraction, saying that, reduce this from the original mesh. So border B0 is actually hollowed mesh. Let's see that in action. So let me clear terminal, and example 6 is this one. So you see that that's exactly the same geometry as example 5, but in this case, this is actually reduced. So this is hollow, this is empty. And then the maze is nicely generated, and this is really super nice. Later on you will see that it's how easy it is to solve a diffusion or convection equation on this kind of geometry, and you can assign different boundary condition to that. For example, the diffusion, the spreading like some chemical species around, and this is really like the kind of notation, the kind of code that you need to generate such meshes. And the hint is actually embedded inside this minus sign, negative value for build mesh. So empty, making a part of the mesh empty. As simple as that. And then the 7th example is the same code, but this time two boundaries. So two boundaries with, a negative number. In this case, it is a bit more complicated because, we want to have like, let me show you first the code, and then I will tell you why it is like this. So example 7. So you can see that now we have two holes here. And for that, we have shift up. That is actually the number that these two holes are, above the horizontal line. In this case, for example, the y-axis, above the x-axis, along the y-axis. So this is the value that is defined by shift up, and shift horizontal is actually the value that these two holes are deviated from the central line of this semicircle. So this is then the parametric definition of that, and then we will have two elements here. But very similar to that, we have another example here that comes from the FreeFEM example. So this is from the FreeFEM developers. As you can see, we have one border that is a complete circle, and then we have 4 borders here and then 4 borders here. So for 2 different rectangles, 2 different squares inside that. So let me run example 8. And this is a kind of condenser that in FreeFEM documentation, some equations are solved in this for heat dissipation and heat diffusion, sorry. But in this case, you can see that we have the whole circle, a complete circle defined by C0, and then we have also 2 integer numbers here, C1 and C2, that are passed to these borders. So the one here, for example, has C1, and this one is C2, and they are assigned with really random numbers, 99 and 98. As I said, it's really important to be just different, and it's not really important. These numbers do not have any meaning at all. So one parametric definition here, as you can see, it starts from 1 to y3. So y3, y6, and 1 is actually here because the central line is here for circles, for this kind of curvy domains. And then you have C1, so C1 is this one, and C2 is this one. So this is actually the way that is defined, and then you can see here that there is only one of these borders are differently defined. So from 1 to 2, and then you can see that for only this one, it's actually 20 is defined here. If I change it to positive 20, so plus 20, you can see that the C2 is actually filled with some mesh elements. It's because it should be defined counterclockwise in FreeFEM when you want to have something that is actually reduced from the other mesh, and that's why this is defined like this here. And then, 2 more examples here. That is, again, another one for the borders. So this is a kind of L shape. As you can see, as I said, it is not only for like simple geometries, but it can be for more complex ones, like, so something that has an L shape like this. So this is really like starting from here and going through all these boundaries, and even more complex shapes can be defined parametrically using this kind of notation, which is quite powerful in my opinion, especially for prototyping, creating sample mesh files. It can be used as simple as this. And then another one, this is another type of mesh generation that is used by kind of functions. In this case, again, border is defined here, and borders are functions. As you can see here, it's a kind of notation that is inside the curly brackets. And then x and y are defined, but in this case, x and y coming from another function that are defined here. So this is actually combining the notations of syntax of FreeFEM, allowing defining various functions inside this border. And when this is defined, for more complex mesh files, that is actually this kind of parametric design, you can see that it can be used to create more complex, curvy domains or boundaries or borders, let's say. So in this case, the first time I run it, this is actually for loop here that changes I from 1 to 30, and then you can see that I build a mesh using C and minus I 5. So 5 times more than I. So here, each border is actually, or all the borders, so this is one border only, all the borders are defined like with only 5 elements, as you can see. But then as I progress, I need to press enter, because this is actually the magic of this weight equals 1, because it has waited for me to press enter. When I press enter, it goes on, and then I will be 2, meaning that the mesh will be generated with 10 elements on the border, and then so on and so forth. So let's do that and see what happens. So this time you see that it is with 10 elements and then 15 elements. As you can see now, it is getting completed, and then 20 elements, and now we will have, as I move on, you can see that we will have a heart. So actually, for defining more complex parametric design, we need to provide it with enough elements on the border actually. And then as the last example, that's as I said, this is probably, can be considered as the most advanced case, because this can be more practical in projects with external mesh with more complex geometries. So meaning that for more real world research, when you want to have an external mesh and you load a mesh and you work on that. So in this case, we have a mesh externally defined here using Gmesh. You know, in one of the previous series in Talks Riders, we did something very similar to this. So we had an external mesh, and then we loaded it inside of FreeFEM, and we solved a heat diffusion equation on it. And in this case, you can see that we have a mesh here. Let me plot it using Gmesh so you can see the mesh actually. So this is the mesh. As you can see, there are different labels for the mesh that can be used later for the boundary conditions. So this is, for example, for a CFD simulation. So in this case, this is the inlet, and this is the outlet and the walls, and this is a source of reaction or source of heat or something similar. And then, these are the numbers that we can refer to those boundaries inside a FreeFEM code. So that's very similar to the label that we define for borders for a build mesh function. And then, the way that we can load it in FreeFEM is quite simple. As you can see, we have a red mesh function that accepts the path to the mesh file, and then the mesh can be built upon that function. And when we plot it, so FreeFEM, and then I want to run example 11, load external mesh. You can see that it also reports some stuff about the mesh, but this is actually the mesh loaded inside FreeFEM, so we can go on with that in the finite element computation. So that's all the thing that I wanted to say in this video for various aspects of 2D mesh generation inside FreeFEM. I hope you find it useful. In the next video, we talk about 3D mesh generation, which is more or less the same, although that's more complicated. So in real research, we usually load the mesh ourselves externally from an external mesh file like this. But there are really cool features in FreeFEM that for simpler cases, there is always a way to, create a mesh directly inside FreeFEM. As I said, I hope you find it useful, and see you in next videos. Bye.